Unexplained gaps in the sun's spectrum. Why some colors remain a mystery. The sun, despite being the most studied star in the universe, still holds secrets. High-resolution analysis of its light spectrum reveals unexplained gaps, colors missing from its array that scientists haven't fully accounted for. For over 2 centuries, dark lines in the solar spectrum, Fraunhofer lines, have been linked to elements absorbing light at specific wavelengths. Yet, despite decades of advanced spectroscopy, some of these lines remain unidentified, challenging our understanding of stellar composition. The Fraunhofer lines, stellar fingerprints. The sun emits light across the full spectrum, but it isn't uniform. The brightest part of the spectrum falls within yellow-green wavelengths, even though the sun appears white to the human eye. Scattered throughout are dark bands called Fraunhofer lines, named after Joseph von Fraunhofer, who documented them in 1814. These lines are created when atoms and molecules in the sun's atmosphere absorb photons at certain wavelengths. Each element has a unique absorption pattern, making them a tool for determining the composition of stars, galaxies, and even planetary atmospheres. Why some lines remain unexplained. Most of these lines have been mapped to known elements like hydrogen, helium, oxygen, sodium, calcium, and even trace amounts of mercury. However, hundreds of observed absorption features don't match any known chemical fingerprints or synthetic models of the sun. This isn't a simple oversight. Several factors contribute to this puzzle. Incomplete atomic databases. The reference data of atomic and molecular spectral lines is still growing. Identifying unique fingerprints requires extensive testing and verification, particularly for complex groups like iron. The sun's dynamic atmosphere. The sun isn't static. Convection currents and chaotic magnetic fields constantly shift and interfere with the absorption patterns, making them hard to model accurately. Complexity of stellar evolution. The elements in a star are a measure of its age. The sun's composition is the result of billions of years of nuclear fusion, scattering, and reincorporation of heavier elements. Implications for stellar science. The missing lines aren't merely academic curiosities. They remind us that our understanding of stellar processes remains incomplete. When the universe began, it was nearly all hydrogen and helium. Stars forged heavier elements in their cores, then spread them through explosions. The sun's elemental composition and the gaps in its spectrum are clues to how stars evolve and shape the universe. The persistence of these unexplained features emphasizes how much we still have to learn about even our closest star. Better instruments, growing databases, and improved models are helping us close the gaps. But the sun is unlikely to give up all its secrets anytime soon. This ongoing exploration is not just a scientific pursuit, it's a testament to the universe's unending complexity.